Hello and welcome back. The purpose of this video will be to apply the concepts we've been learning in Chapter 14 to a problem from your openstax textbook. So first of all, let's just summarize for a moment. Remember that Chapter 14 is focusing on the subject of heat. Heat gets the symbol Q, and heat is a type of energy that is transferred due to a temperature difference. It can be transferred via conduction, convection, or radiation. Calorimetry is the study of how a material changes when heat is either added to it or removed from it. So remember, if the material is not at a melting point or a boiling point and you add or remove heat energy, then the temperature of the material will change, and that is governed by Q is equal to mc delta T. If the material is at a boiling point or a melting point and you add heat energy Q or remove heat energy Q, then the equation that governs that is Q is equal to mL. And L can be the latent heat of fusion if you're between solid and liquid, and L can be the latent heat of vaporization when you are in between liquid and gas. The lowest energy to highest energy states for materials is solid, then liquid, then gas. So solid's the lowest energy, gas is the highest energy, and liquid is in between. If we have liquid water at 0 degrees C, so liquid at 0 degrees C, and we remove heat from it, notice it's at its melting point. If we remove heat, then the phase is going to begin to change. But if instead that liquid water at 0 degrees C is having heat added to it, then the temperature begins to increase. So remember that the higher energy state is going to be from solid to liquid to gas. So when we're removing energy from liquid, it's moving towards solid. When we're adding energy to liquid to solid, it's moving toward liquid, and vice versa. So we have to keep that in mind, that the lowest energy state to highest energy state is solid to liquid to gas. So now what we're going to do is look at a problem from your textbook, and this is going to be 14-8 from the openstax textbook, and it reads as the following. The number of kilocalories in food is determined by calorimetry techniques in which the food is burned and the amount of heat transferred is measured. How many kilocalories per gram are there in a 5.00 gram peanut if the energy burning from it is transferred to 0.500 kilograms of water held in a 0.100 kilogram aluminum cup, causing a temperature change of 54.9 degrees C? B, compare your answer to the labeling information found on a package of peanuts and comment on whether the values are consistent. So it's important to note here that kilocalorie, in the units that we are going to be looking at here, is sadly the same unit as the calorie on your food label that you read in grocery stores. So I have that written down here on the bottom, that the kilocalorie, KCAL, is the same as the calorie unit you find on your food label in your store. So the food labels in stores already have units of kilocalories, but sadly they just refer to them as calories. So I've taken some of the information we're given in the problem and I've summed it up here on the left-hand side of the board. So the mass of water that we're going to be heating is 0.500 kilograms. The mass of aluminum is also going to be heated. The aluminum and the water are going to experience the same temperature change. So the mass of the aluminum, 0.100 kilograms. The temperature change for both of them, 54.9 degrees C. Notice I don't need any subscript on the temperature because the aluminum and the water will both experience the same temperature change. The specific heat for liquid water, which is what we're dealing with, 4186 joules per kilogram per degree C. The specific heat for aluminum, again taken from table 14.1, as is the water, 900 joules per kilogram per degree C. The conversion back and forth between kilocalories and joules is that 1 kilocalorie is equal to 4,186 joules. So I can form a ratio with these two values to change the units from the joules that I will be getting to the kilocalories, which is what we're asked for. So summarizing what it is we're asked for here in part A, we want to know how many kilocalories per gram when the material goes through a temperature change, and then we also want to compare the value that we get with what we read on a label. So down here at the bottom, I've went and retrieved that information from a Google search, and I found that 33 grams of dry roasted peanuts is the same as 200 calories. And so remember that the calories on the food label is really kilocalories. So I've written that right here. 33 grams is equal to 200 kilocalories. So let's go ahead and get started then. We want to see how much, remember that kilocalorie is just another unit for heat. And so we're using units of joules to begin with. And we are told that the amount of peanuts that is burned to experience this temperature change for the water and for the aluminum is 5 grams. So the mass of peanuts is 5.00 grams. So let's go ahead and figure out how much heat energy is released by the peanut as we heat up the water and the aluminum. And then we can take that heat energy and we can divide it by the mass of the peanuts, and then we will know how much energy per gram we have, and then we can convert that to kilocalories from the joules that we will be using. So A, the total heat energy that will be released will be going into heating up the water and heating up the aluminum. So you can see the total heat energy released by burning the peanuts is going to be equal to MC delta T for the water plus MC delta T for the aluminum. So we know all of these values, so we can simply plug them in. So Q is equal to the mass of water, that's 0.500 kilograms, times the specific heat of water, that's 4186 joules per kilogram, times degrees C, times the temperature change of 54.9 degrees C, plus the mass of the aluminum, 0.100 kilograms, specific heat of the aluminum, 900 joules per kilogram, times degrees C, times the change in temperature, 54.9 degrees C. So we can figure out the total amount of heat energy that is released by the peanuts as they are burning, and so 0.5 times 4186 times 54.9 plus 0.1 times 900 Okay, I almost have it here. We get a value, a total amount of heat energy necessary of 119,846.7. And you can see the kilograms is going to cancel and the degrees C is going to cancel, and there's going to be units of joules. And let me just quickly check, because that seems like a very large number, but let me just make sure that I'm getting the same thing by a second calculation. Yes, this is indeed the value. And so this is the total amount of heat energy that is released by burning this mass of 5 gram peanut. And so we want the energy per gram. And so if I divide this both sides by the mass, then I have the energy per gram. So Q over M is going to be equal to 119,846.7 joules divided by, and this is the mass of the peanut. This is 5.00 grams, and we do want it in grams, not per kilogram, but grams. So this is 5.00 grams. Now we want to convert from joules to kilocalories. So we already have that equality right here. We want to get rid of joules, so we're going to put joules in the denominator, and we want kilocalories in the numerator. So there it is. And so we're going to take this number and we're going to divide it by 5, and then we're going to divide it by 4186. And what we get is 5.73. And the units, we can see the joules will cancel, and we'll have units of kilocalories per gram. So that's exactly what we wanted in part A. We want to know how many kilocalories per gram are available being measured using calorimetry techniques in a laboratory. And now we want to compare that with what the label is telling us. So the label tells us that there is 200 kilocalories in every 33 grams of peanuts. So in part B, we have Q over M as, and I'm going to put a prime on that Q. This is going to be 200 kilocalories. This is from the label, a little Google search, divided by the 33 grams. So that's where we're getting that information. And so when I want again in kilocalories per gram for the units, so 200 divided by 33 gives us 6.06 kilocalories per gram. So you can see the numbers are very close. We wanted to compare with the label. We can see that using the techniques in the laboratory where the 5 grams of peanuts are burned, and seeing how that heat energy heats water and aluminum, we can figure out how much energy per gram is available from the peanut, and then what is expressed on the label is very, very close to what we see measured in the lab. So this gives you an idea of how to apply our calorimetry techniques to a real problem from your textbook and a real problem in mainstream. So we will see you next time to further our discussions in Chapter 14, working some more problems. Thank you.